Welcome, everybody. Hello, GM, and welcome to week 2 of the Explore Expander Bootcamp. Welcome, welcome. Say hi in chat. And today we are welcoming Alin from Aptos Labs. I'm going to quickly send him an invite to come to the stage as we will be covering zkLogin architecture. Just a reminder, this is going to be just the first of 2 workshops, and later today we will have Wei Dai, who's going to be doing an introduction to private transactions. Hey, Alin.
Hey, I'd like the link to that workshop as well. That would be great.
Absolutely. Happy to add you to the calendar.
Nice.
Um,
Thanks for having me.
No, absolutely. Everybody will be having a really interactive workshop. Alin have asked me to interrupt him throughout the workshop if you have any questions. So make sure to voice them in chat. Doesn't matter where you do so, either in the chat section or the questions area. And I will make sure to bring them up as quickly as possible to Alin as he ends up replying. In the meantime, Alin, feel free to share your screen, share a few words, and take it away.
Yeah, let's see. The hardest open problem in computer science is sharing your screen. So, okay, I think this works. Great. So this is probably the most difficult part of the presentation. All right, so my name is Alin. I am the head of cryptography at Aptos Labs. We are a layer 1 blockchain proof of stake. We've been live since October 2022. And today I'm going to tell you about a feature that we built that we hope more chains will adopt. And this feature is called keyless blockchain accounts. And it's a way to get a blockchain account to be secured not by a traditional secret key or a mnemonic, but by a traditional Web2 account, like your Google account, Apple, or Facebook, or any OpenID Connect OIDC account. So we're kind of taking sign in with Google and turning it into signing transactions with Google. And that's what this talk will be about. All right, so let me just give you kind of a broad overview of what is a keyless account. The way I think of this is that your blockchain account is your Google account. So there are no long-term secret keys that you have to manage or worry about. Which means that your blockchain account is as hard to lose as your Google account, and it's also as secure as your Google account. And in particular, we do this without making any use of multi-party computation custody. So we don't have 5 servers somewhere that actually store a key for you. We have no such thing. It's just you, Google, and the blockchain. And again, in this talk, when I say Google, I'm really going to mean any OpenID Connect provider, but I'm going to use Google as a canonical example of that. All right, so now that we kind of know what we're trying to do here, why do this at all? Why enable this keyless account feature on Aptos and on other blockchains? And the way I think about it is we're trying to expand seamless access to cryptocurrencies. So cryptocurrencies, as you guys know, are a little bit hard to use. Even expert users kind of tend to lose access to their wallet. And so features like keyless hope to put a little bit of a dent in that. But beyond kind of losing your account in general, if you think of kind of the flow of using a cryptocurrency, especially as a beginner user, it has a lot of friction. So you have to install a wallet. People don't even know what this wallet is and what it does. They're confused about that. And then they're further confused by the fact that they're told to write down this mnemonic and they don't understand its importance. And as a result, they end up kind of losing it or tossing it away. And they kind of, might have bought $100 and now it's all gone. And maybe they never engage with the space again because they think it's kind of easy to lose money. And then even if they get past these 2 phases, they see these transaction prompts all the time, which are kind of technical and potentially confusing. And if they try to transact from another device, they experience a lot of pain switching their secret key from one device to another. And lastly, there are phishing attacks. So many users are tricked into pasting their mnemonic or secret keys onto forums. And more recently, even on Aptos, but also I think on Ethereum, we see these address poisoning attacks where if you pay an address, another bot pays you from a similar address, sort of to trick you into copy and pasting the bot's address when you send the next payment. So this is very, very fascinating stuff. And the TLDR is that existing kind of cryptocurrencies applications are pretty tough to use. You gotta know what you're doing. And so keyless accounts hope to make a dent in this. So keyless-based applications can actually be walletless or promptless. They don't have to be, but they can be. You have no mnemonics that you have to write down. When you go to a DApp like an AMM, you can sign in with Google, and now you have your account for that DApp. And this makes it, as a result, very hard to lose your account, right? As long as you're in possession of your Google account, you're in possession of your blockchain account. And another consequence is that you get cross-device functionality seamlessly. As long as you can sign in with Google from your phone, you can recover your blockchain account. And there's also other goodies. As I'm about to show you soon, a keyless blockchain account has an address like any blockchain account, and that address is derived from your email address, for example. And so now we have this opportunity of potentially sending payments to email addresses rather than clunky 32-byte addresses, which can be mistyped. And there's also other interesting opportunities, which is that when you have these blockchain accounts backed by a Web2 account, these Web2 accounts could hopefully in the future be even something like Coinbase. And you might be able to prove things that, for example, Coinbase did KYC for your account. And so you're perhaps allowed to receive an airdrop or to engage in a particular use case. So for this reason, I think enabling keyless accounts is really, really exciting. And in fact, we have done so on the Aptos network since January 2024. And the kind of the point of this talk is to get more people to think about this approach and how they can leverage it. So I think, you know, this is not a panacea. There's also objections to keyless accounts. And the most often heard objection from my perspective is, I don't want to trust Google, or I don't actually trust Google. And I think that's fine. It's a very reasonable objection, and it's something to consider, because Google can indeed steal your funds behind this keyless account, right? So your Google account is your keyless account, but that actually means that your security is based off of Google security. Some people might think this is a feature, other people might think this is a bug, right? So you make that own choice for yourself. What I will say is that there's been billions of dollars in cryptocurrency assets that were lost, and some of those millions of dollars were lost by power users like you and me probably. It could be that you are a responsible power user, but think about that carefully. And if you are self-custody, that's fine. Keyless is not built for you after all. There's power users that should probably not use it. But also, you don't have to just trust Google, right? You could choose to trust any 2 out of 3 OIDC providers, for example. So Google could not steal your account on its own. It would have to collude with Google, with Apple, or with Microsoft, for example, to steal your account. So in general, there are sort of mitigations against these objections. But I did want to highlight this, since this is actually a very often brought up point by cryptocurrency enthusiasts, and I think it's a fair point. All right, so now that we've kind of talked about why enable or not enable keyless account, let's just talk at a really high level, how do they work? So a keyless account, its address is derived from a couple of things. First, your email address. Second, the identity of the managing application. So your address is actually associated with an application like a web wallet or a DApp. So think like uniswap.org or something, or a web wallet, like imagine MetaMask had a web wallet, your address could be associated with MetaMask. And what this is really getting at is that keyless accounts are app specific, right? So a lot of you are used to this world where a cryptocurrency account is just a secret key and it has a public key and you sort of put it in a wallet and that wallet connects you to many DApps, right? Well, in this keyless world, each DApp is its own account. And of course, you can have a wallet that is its own account too, and then you could connect that wallet to traditional DApps as well. So you can kind of get the benefits of both worlds. You can have a web wallet that is using a keyless account and connects to existing DApps, or you can build DApps that have no wallet functionality whatsoever. They're walletless and have their own keyless account associated with them, right? And in this last mode, I'm going to call this the walletless mode. What's really important is that if you start a keyless account on medium.com, let's say medium.com had a cryptocurrency feature where you could tip writers, then medium.com cannot do anything to steal the keyless account for some other website like uniswap.com, right? So these accounts are very well domain separated. That's what I mean by they are app specific. And this is what actually allows for this walletless flow that is promptless. Right, so the DApp owns your account, so it can do whatever it wants to it, but only to it, not to other DApps accounts. All right, so now that we know what a keyless address account is and how they're tied to an application, whether it be a web wallet or a DApp, how do you sign transactions for such an account? And at a really high level is you don't actually. Google signs them for you. But to prevent leaking your email address on chain, you're going to use some zero-knowledge proofs to hide that signature from Google from the chain, but instead prove that you know such a signature, right? And in particular, what Google signs over is a couple of things: the transaction hash, your email address, and the application ID, right? And this way, the blockchain can verify, let me get this pointer here, the blockchain can verify that this email address and this application ID is what your blockchain address is derived for, and Google has signed over it and the transaction hash, and can authorize the transaction. And of course, lastly, we need a splash of zero knowledge for privacy. So we need to hide your Google email address and the application ID from the blockchain, but we also want to hide the blockchain address and your transaction activity from Google. It's kind of two ways, right? And this is at a really high level how keyless accounts work. All right, so now I think I'm ready to kind of describe to you the flow. So imagine you're a DApp developer. You want to write a really cool dream DApp that you've been thinking about a lot. I'm going to depict it with this phone icon. And you're sitting here on your desk and you're thinking about how to do it. And you want to use keyless accounts. The first thing that you have to do is a little bit of a bureaucratic step. You kind of have to register your DApp with the OIDC provider. So with Google, let's say. So you go to Google, you say, hey, I'm going to register a web application. Its domain is www.metamask.com. It's going to be a web wallet. And after you do that with Google, Google gives you this so-called client ID, which is an identifier that's Google specific for your DApp. And now when your DApp is live, you've deployed, let's say, metamask.com. Oh, and I should say, by the way, this client ID is the same application ID I mentioned earlier that's used to derive the keyless address together with your email address. All right, so now that you have this client ID and you've deployed your DApp online at metamask.com, let's say, your users are going to go to your DApp and they're going to be taken to a sign-in with Google prompt when they sign into your DApp. And importantly, that URL actually contains the client ID. So the DApp redirects you to a Google URL with this client ID. And most crucially, what the DApp can do is it can actually put any arbitrary data in that URL. And this is really key, because what's going to happen is if you successfully sign into Google at this URL with this arbitrary data in the nonce parameter, what Google is going to give back to you is a signature of you having successfully authenticated. And the signature is going to be over the account that you authenticated with, the application that you authenticated in, so metamask.com, let's say, and this arbitrary data, right, that the application specified. And importantly, because this is a digital signature under Google secret key, whose corresponding public key is known, anybody in the world who has Google's public key, any third party, can verify the signature, right? So when we kind of sat down and thought about this a while ago, we realized, well, this is kind of curious. So there were a lot of MPC companies that were kind of leveraging this to authenticate users to their MPC system using their Google account, because the MPC system was storing the key for those users. But it's kind of immediately obvious if you look at this is that you don't actually need the MPC system at all to store any keys, because what you can actually do is, first of all, like you can have the blockchain verify these signatures from Google, and second of all, the application that you sign into can be something like a wallet, and third of all, the arbitrary data that you sign over can be a transaction, right? So if I sign into a wallet and I successfully do so, then in that process I can implicitly kind of trick Google or any OIDC provider to sign a transaction for me, right? And then I can take the signature and make it publicly verifiable on chain, right? So this slide is the key idea behind keyless accounts.
A few questions now
Great.
as come in.
Fantastic.
What if Google refuses to give you an OIDC account to operate your DApp?
What if Google refuses to register your DApp with a client ID?
Yes, the question as it was written was like, what if Google refuses to give you an OIDC account to operate your DApp?
It's not that Google gives you an OIDC account to operate your DApp. It gives you a client ID. That's all it gives you. You have to have a Google account to register the app, and then you go into this Google Cloud Console and you get this client ID. And yes, indeed, Google is a centralized party who can refuse to do so. So that can be a problem, absolutely.
is there a recovery option in case Google blocks the OIDC of the registered app?
Is there a recovery option if Google blocks the client ID of the registered app? So in the way we designed keyless, yes, we have this recovery mode, which I'm happy to discuss later. But basically, if at some point Google refuses to provide these signatures for your app's client ID, because maybe Google doesn't like you, we kind of have a way to recover. I'll give you one simple way to recover as an example. One simple way to recover is in recent, I think the last year or two, there's been a lot of excitement about the ZK email approach, where you can prove you own an email address, right? And so instead of giving a signature from Google on chain to access your blockchain account, you could kind of build a 1 out of 2 account where you either give the signature from Google or a ZK email proof of ownership of the email address as an alternative, right? That's one way to do it. We have another way that we propose where if Google refuses to sign over this client ID, then we can have a recovery service that you can sign into with a different client ID. And this client ID can act as an override for any client IDs in the system, for any application in the system. So the rule is you either get a signature over the same user and client ID as in the keyless address, or over the recovery services client ID. So as long as Google doesn't ban the recovery service, you can get back access to the funds. I'm not sure if that made sense, but I can spend more time discussing that.
Another question is, what is being used for ZK? And if you can please elaborate on that.
What is being used for ZK? I presume the question is around the particular choice of proof system.
Yes.
Yeah, so I was going to touch on that later in the talk, but real quickly, we'll use GRAT16 zero-knowledge proofs over BN254 elliptic curves. Our circuit size is 1.5 million R1CS constraints. Proof verification time is 1.2 milliseconds. Proof size is 288 bytes, I think.
Another question from chat. For each new transaction, do you need to ask Google to sign a new message with the nonce transaction hash?
Good. I'm also going to get to that in a second, so I'll defer that. Yeah.
All right. Okay. I'll stop here and let you proceed, and we'll interrupt in a bit with more questions. Everybody, keep posting in either the questions or the chat area.
These are great questions. People are clearly looking ahead. Great. All right. So as I was kind of hinting earlier, what we're essentially going to do to enable a keyless account is we can send the transaction for this keyless address and reveal the signature from Google and the client ID under the address and the email under the address. And then the blockchain could simply verify that the signature is over the same email and client ID as in the address and the transaction. And of course, for this, it has to actually match the address with the email and client ID in the request. But like I kind of hinted earlier, there's a big problem here. We are revealing the email address and the application ID to the blockchain. So we really want to avoid that. And so what are we going to do for that? We're just going to sprinkle some zero knowledge. So as you can see, this is a very simple change in the slide. It's a very complex change to actually implement. So instead of giving the OIDC signature, the client ID, and the email, we're going to give just the zero knowledge proof. And instead of verifying a signature, we are actually going to verify a zero knowledge signature of knowledge. So we're going to verify the zero knowledge proof pi. And the public statement will be the keyless address, the transaction, and Google's public key. And what the zero knowledge proof argues is that there exists a signature that verifies over some email address and some client ID over this public transaction. And this email address and client ID are the same, are what's sort of used to derive the address in the public input. So that's what the zero knowledge proves. It says, hey, I know a Google signature, which is over the same email address and client ID as in your blockchain address, and it verifies. Okay, and the problem is that this is slow. So in our case, I think we were able to write the circuit in 1.5 million constraints. It would take, I think, 6-7 seconds to prove on a commodity laptop. So you could imagine that in the browser, it's going to be 5 to 10 times slower. So it's rather impractical to compute these proofs on the client side. So we have to use a prover service. And this is kind of annoying for us, and it's sort of an open area of research that we're working on, because the prover service, as you can imagine, has to get the secret witness as input. So the prover service is not privacy preserving. And there's new techniques, collaborative SNARKs, and so on that could help to maintain privacy, and we want to explore those. But nonetheless, we modulo the prover service. The blockchain does not learn anything about your email address or the application you're engaging with. Now let's get to the second problem that was just asked in the question. It seems like Alice has to compute 1 ZKP per transaction in order to transact, and the blockchain verifies 1 ZKP per transaction as well. Can we make this better? The answer is yes, we can. We're just going to use a layer of indirection. Instead of signing the transaction, we're going to sign an ephemeral pub key, and then with that ephemeral pub key, we're going to sign as many transactions as we want. So now you can think of the zero-knowledge proof as a digital certificate, kind of binding your blockchain address to this ephemeral pub key together. So it says, hey, I'm delegating signing rights for this blockchain address to this EPK, right? And I'm doing that by virtue of there being a YDC signature from Google over the EPK and the addresses pre-image. Yeah? And so now we can just include the ZKP and the ephemeral pub key and a signature under the associated secret key over the transaction, right? And so the validation logic is also augmented to verify this ephemeral signature over the transaction. And that's how we take care of the question in the chat. And I also want to point out that this ephemeral key pair that the user generates can be a passkey. And another thing I want to point out is that notice that the prover service that I talked about earlier does not actually get access to the ephemeral secret key. It just sees the ephemeral pub key. So the prover service cannot actually steal your account. It can see what you're doing if it's not built in a privacy preserving manner, but other than that, it cannot steal your account. All right, so that takes care of efficiency. What about leakage? So if you look at the address, the way I wrote it here, it can actually be brute force. So these client IDs are public and email addresses are low entropy. So an attacker given an address can kind of run through a lot of guesses for the email and figure out whose address this is. So we're going to solve this by, instead of just hashing the email and the application ID, committing to it using a random blinding factor that we call a pepper. So this will be 256 random bits. And the key challenge here is that if you lose this pepper, you won't be able to transact. So if we're not careful, our initial keyless dream will not be keyless anymore, because you're going to have to remember this pepper in order to unblind this address inside your zero knowledge relation. And so how can we implement this pepper service in a keyless fashion? And the answer is actually very, very simple. The user can authenticate themselves to a pepper service using Google, once again, using the signature from Google, potentially even in a privacy preserving manner. And the pepper service can give the user its pepper, right? So there's now no way for the user to lose this pepper on their own. The user is effectively trusting a pepper service to maintain the pepper for it. So now there is some custody trust in this pepper service in some sense. Once again, the pepper service, like the prover service, cannot steal your account, because it's not enough to have the pepper. You have to have the signature from Google, which you cannot get. But the ephemeral secret key. But the pepper service, if it disappears off the face of the earth because it was nuked or something, all of the users would be locked out. So durability of the peppers on the service is very, very important. All right. Yeah, is there a question?
More questions, if that's
Yeah.
fine. So can we use Google Sign-In as part of a DID in Web3?
Can we use Google Sign-In as part of a DID in Web3? I mean, that's a very broad question. I'm not sure how to even begin to attack that. I guess that's what this talk is about, is to use Google Sign-In to establish blockchain accounts. I'm not very familiar with the DID standard and sort of the nomenclature there and everything that they're trying to achieve. But if you make the question more concrete, I can try and answer.
All right, that's for Papu. So then, Papu, if you want more details, please, if you can elaborate on your question, that will be amazing. Another question from Iaso is, what's the APK expiration? Does it have a session limit?
Yes, exactly. That's a really good question. I'm sort of hiding that detail here. So when I say EPK, I'm kind of trying to implicitly say EPK and expiration date. So think of the expiration data as being part of the EPK. Yes, it does have an expiration date, and it's set by the application, right? And it can be application set, and there can be a limit on how long into the future these things can live.
A follow-up question from Walid is the circuit open sourced?
Oh yeah, it's open source. Yeah, I'm going to give you guys a link at the end. We firmly believe in this. We want people to play with this, and we really want to explore the viability of this approach for the community.
Great. And last question before we continue is, what would be an alternative to the Pepper service?
Yeah, I guess an alternative is pick a PIN code, like a 5-digit PIN code if you want. You know, that won't provide much brute forcing protection, but it'll at least provide some. They're really, you know, you just have to think, how are you going to blind this address? Typically, cryptographically, the only way we know how to do these things is to use a blinding factor that's high entropy enough. Like maybe you don't want 256 random bits, maybe you can use less. Maybe that makes it easier to remember. Whatever you do, though, you better not lose it, because you're going to lose your account, which is why the keyless infrastructure that we deployed comes with an SDK, which uses a Pepper service by default for our users. Of course, application developers can do what they want for their users, including using an application-specific Pepper, but we don't encourage that, because durability of, I'll talk later how the Pepper service can work, and durability of actually a secret key that the Pepper service could manage is very, very important.
A follow-up question for Peppers is, do you have any recommendations about Peppers on ZK identity topic? Hopefully seminal ones that are must-read, or even for this zkLogin protocol, a white paper.
Sorry, let me go into the chat, because I'm not sure I could parse that.
Yes, that's on the very top. Yeah.
ZK identity. I don't know what people mean when they say this. This is such a buzzword. But look, I would recommend you read a couple of things. I would start with the open pubkey paper, which is at the let me, can I type in this chat?
You can post and tag, yeah, in the chat section on the right side.
All right. So I would say this. One, OpenID, open pubkey paper, search ePrint. There is Aptos Labs' zkLogin paper. There is the Aptos 61st improvement proposal. This is linked in the slide. And this will describe kind of the state of the art on this keyless approach. Now, ZK identity is, again, kind of a buzzword. It's kind of hard for me to know what you mean there. I would also look at anything having to do with ZK email. I think that's also a very exciting line of work. There's, I don't know, other people can weigh in.
Yeah, that should be enough for now. Thanks.
Yeah. Okay, so I will expand more on the Pepper service towards the end of the talk. I'm taking my time here since we kind of have an hour. All right, so again, the problem we fixed was that the address leaked your email address. The blockchain address leaked the email address. And this should be problem 4. Google sees your EPK, right? Remember that in this flow that I kind of described here, Google kind of gets the EPK as a nonce, right? And so this is kind of bad, because when Google sees the EPK, it can track on-chain the transactions that use the EPK and tell what Alice is up to on-chain. And we don't really want that. You know, we don't want Google to figure this out. And how do we do that? So the answer is actually extremely simple. Instead of putting the EPK in the nonce field, we're going to commit to the EPK using another blinding factor. Fortunately, this blinding factor is not a long-lived one. It's a very short-lived one, right? So the DApp generates it, creates this commitment, and feeds the blinding factor as a secret input to the zero-knowledge proof, right? And this doesn't have to be remembered. And basically, that's it. At a really high level, this is the keyless architecture. I will run you through a flow later on so you can see all of the components work together. But before I do, let me just reiterate what I said earlier about the ZKP implementation. So when we set out to do this, our goal was to come up with a design where the verification time of these keyless transaction signatures is very, very fast. So let's say 1.5 milliseconds, and the proof sizes are small. So we ended up GRAT16 over a very small curve, BN254. To implement this, we use Circom, and there's a circuit repo link here, and I'll share the slides with all of you later. It's, I think, 1.4 or 1.5 R1CS constraints, same number of R1CS variables. One thing that's interesting about our circuit is that we have some cute polynomial-based protocols to do string operations like substring matching to ensure that the email address is somewhere in the message signed by Google, for example. And we did a MPC ceremony for the trusted setup in GRAT16. We have a contributions repository. There were 140 participants over 1 week. This took place in February 2024. We used this potion tooling from Privacy Scaling Explorations. And we have this prover service, which uses IDEN3's rapid SNARK repository. We kind of hardened that. And we have a Pepper service that's using a BLS-based verifiable unpredictable function to derive users' peppers. And I'll tell you how that works in a second. All right, so this kind of brings me to the end of the talk, but I will still give you a high-level flow of keyless later on. So the one thing I want to say here is that when I think of cryptocurrencies, I'm kind of terrified of UX. I think UX is key, and I think good UX is keyless. So that's one message that I want you to think about at the end of this talk. Everything I've presented is open source: Pepper, Prover, Circom code, blockchain validation logic, governance on chain for keyless accounts, and so on. It's been live on the Aptos mainnet since June 2024. We've seen 420,000 keyless accounts and 17 million transactions. There's other things that we want to do, like we want to make the Pepper service privacy preserving. If you recall, the user has to authenticate themselves to the Pepper service in order to get their Pepper using a JWT, and so the Pepper service actually learns who the user is. But once again, there's a hope to use zero-knowledge proofs to avoid this. And we have some ideas about that. You can click on this link. There's also another interesting work stream to move the Pepper service on top of the blockchain validators. So in particular on the Aptos network, our blockchain validators are able to share a long-term secret and compute verifiable unpredictable functions with that secret for a on-chain randomness beacon that we implemented. And we could actually hope to leverage that to implement the Pepper service as well. So that would be kind of exciting because it would be one less deployment complexity associated with keyless accounts. And it would also be a step in the right direction for the privacy preserving Pepper service. Obviously, like anybody in the space, we want to do faster proving, but this is kind of tricky because it cannot come at the cost of slower to verify proofs or exorbitantly large proofs. So in a sense, we're looking for the holy grail of ZK SNARKs. We don't want trusted setups. We want fast provers. We want fast verifiers. We want small proofs. So this is a really great area for research. Please think about this problem. I think it's interesting because most people in the cryptocurrency space, when they think about scaling proving, they think about scaling really large computations, and the keyless computation is not that large, but it's not that small either. You cannot prove it in the browser. And another thing is, if we're going to keep the GRAT16 ZKP and its trusted setup, it would be really nice to figure out how to do it on the validators efficiently, so that basically the Aptos network itself also secures the trusted setup. And external people can even contribute in, but everything's automated and we don't have to do as much coordination to run it. Of course, ideally, we wouldn't have a trusted setup. We would just use a universal SNARK. There's many things I didn't get to discuss. For example, in this talk, I mentioned that these signatures from Google are your transaction signatures and the blockchain verifies them, but under what public key? Under Google's public key. Well, where does that public key come from? It has to be put on chain, and that public key actually changes every 2 weeks, or it can change whenever. And so you actually need to implement an oracle for this public key. And we have done so via our validators, who are periodically polling this URL where Google's public key is and reaching consensus on the latest one. We have this training wheels mode enabled in our prover service, which is there to mitigate against bugs in our CIRCON implementation. So it's not that the blockchain just checks a ZKP, it also checks a signature from the prover service over that ZKP, which vouches for the fact that the prover service itself checked the keyless relation, is satisfied. So that if the ZKP doesn't correctly prove that, meaning the proof can be forged, then the training wheels save us. We have a way to upgrade our circuit on chain if there are bugs. I didn't get to talk about proof non-malleability and its importance here. We also have support for revealing additional data in the signed message from Google so that we can do things like KYC. And we also support zkless mode. In case of emergency, we can kind of disable all of the ZK machinery and have a zkless mode. And other things that have not yet been implemented fully, like the recovery service that I mentioned earlier, and caching for successful ZKP verifications to reduce validation time, and many nuance and details. Some of them you guys already picked up on, the BK expiration date, these application-specific accounts and their implications, how to secure walletless DApps the best, the JSON web tokens, which are at the core of these Google signatures. It's the message format that Google signs, and so on and so forth. And yeah, this is joint work with a lot of people at Aptos Labs, especially the Aptos keyless team, the core team, and geometry research helped us a lot to secure the circuit. And I'll leave you here with a list of developer resource edge, which I've compiled on my website. So please take a look. And there's also some academic references in the slides. This is the open PubKey paper that I put in the chat. This is the Grad 16 paper. And yeah, I guess with that, we have 37 minutes. We can either take the questions, or I actually want to run folks through the full flow of keyless as well.
So before we do that, like a thing that I think the majority of the participants were not able to do is actually scan the code for the slides, because your picture-in-picture pop-up was exactly on top of it. Can you please share the link so we can make it available within HackerPack? It is a place where
Oh, in the chat?
Yeah, if it's possible.
Yeah, I can put it right. Is this the link? Sure, let me just make sure this is the link. Yeah. I hope that works. Yeah, I think that works. The preview seems to work.
And also the developer resources that are on screen. If you can share these as well, we'll be happy to provide.
This is also great.
Fantastic.
Perfect.
We share these with everybody within the cohort. In the meantime, there were a few questions in both the questions area and the chat, if you want to go over them. And then we can move on. Yeah.
So where should I begin?
You can do with the questions area first, and then the very last messages in the chat section.
The questions area. So
from top to bottom, yeah.
I see, from top to bottom. For the entropy of the on-chain random functions, is it possible to make it secure or need to rely on a server? I'm confused. Is this a question about the on-chain randomness feature, or what entropy is being asked about here? We do have on-chain randomness, but it's sort of orthogonal to this whole talk. Is this question about the VRF behind the Pepper service? Can the person clarify?
It's a question about VRF behind Pepper.
Yeah, good. Okay, yeah. So the Pepper service is VRF based. I will kind of expand on it in this slide. So you see, let's see. Where's my Pepper? Right, so the Pepper is computed as a VRF under this VRF secret key, this VSK over the user ID, which is the email address, and the DApp ID, right? So the Pepper service secures this VSK, and this VSK is the source of entropy. And so when you say, is this secure? Yes, this is secure in the sense that we understand very well that for certain choices of VRF functions, the outputs are indistinguishable from truly random outputs. So in that sense, it's secure, yes. Like if you can distinguish a pepper from, I don't know, uniform random bits that you got from the background radiation of the cosmos or something like that, then that would be great news for us cryptographers, because you would have broken some really hard cryptographic assumption in doing that. Yeah, I hope that answers the question. What's the prover machine spec like? I think it's a T2D with 32 cores on GCP, and I believe the proving time is 1.6 seconds on that machine. Around 400 microseconds, I think, are spent. 400 milliseconds are spent doing witness generation, and the rest is spent doing actual proof computation. What's the EPK expiration? Does it have a session limit? We already answered that. And the rest, I guess we already answered? Yeah.
Correct.
Yeah. I guess for this VRF question, the VRF in the EVM world is very different here. There's no long-term stable key there, if I recall correctly. This is entirely different. There's a service, it has a VSK, it's long-lived, it's never going to change. How you manage this VSK, it's up to you. You can decentralize it amongst a lot of servers. You can keep it on one server. You can use a trusted execution environment. Yeah, and from that VSK, you can derive everyone's pepper.
A couple of questions in the chat section as well. If you can scroll up to Patrick Kish's question from 531. It's this one, the longer paragraph. Yeah.
Please refer to our hacker pack.
No, if you scroll down to Patrick Kish from 531, the question, it's a bit of a longer paragraph right underneath your messages, a bit further below.
This one?
Yes, exactly.
I have 631 here. If there is a service that is able to protect the UID, providing a non-chain SNARK and can only I'm not sure I can parse this fully. Okay, so the sentence structure is like making me dizzy. I apologize. I'll say this. You can definitely implement your own OIDC provider. You don't have to use Google or Apple. So you can use any OIDC provider. And I think actually that's kind of an exciting direction as well. Because it kind of opens a business opportunity. So people can open OIDC providers that manage users' keys for them. It's in a way kind of taking the MPC custody approach and making it more universal, standardizing how the MPC custody should always be done via OIDC. But I'm not sure I can get to this question. Perhaps the author can make the question a little bit shorter, more succinct, more concise. Also add some commas and some periods. That's a really long question.
Yes, everybody, punctuation is key. So
punctuation is key, yeah. Could you not use a regular? Oh yeah, absolutely. You could totally use you could use anything, right? We use the most secure thing, which is a 256-bit uniform random pepper. But you could use anything when you write your keyless app. It's up to you what the pepper is.
Patrick is typing, so I suppose he's summarizing his question.
All right.
A new one just came in from Walid.
Did you test any other proof system for client-side proving, probably, or something? We actually...
There's a second line as well.
Oh, there is? Whoops. I think my...
so the full question, I don't know why it's not showing up, is like, did you test any other proof system for client-side proofing that gives better proving time?
Yeah, we did not, because once again, if you think about the problem constraints, there's only two proof systems that are even viable here. There's Grot16, which has the fastest verifier and smallest proof, and there's Planck, which has comparable verifier and comparable proof sizes. But Planck, we knew we were going to get much slower prover time, so we were not interested in making that slower. So as a result, we didn't really look at other proof systems. Even though you could get faster proving, the verifier time would blow up. And of course, the natural thing the natural objection is to say, well, you should have, because you can wrap those proofs anyway and make them fast to verify. But wrapping is very expensive too. And so that would have led to even longer proofs. It would have completely defeated the point of using a faster proof system like a SNARK, let's say, if you have to wrap. It makes sense in, again, settings where the relation that you're proving is really huge, like a rollup, and so wrapping is not much overhead. But in this setting where the relation is very small, we don't know how to make wrapping kind of make sense cost-wise. And yeah, we did not meaningfully look. If you have any ideas, it would be great to think about. But I think the problem constraints are, we're always interested in smaller verifier time, because that ultimately influences the gas costs for this approach. And if the gas costs are too high, then the UX is bad and users won't use this approach. All right, so let me, this is not editable, could you tell us? Got just to the other team. Are you referring, you're probably referring to Sui's zkLogin, or?
Yes. There was a previous question, I think, also from Sebastian, that touched upon slightly on this, like what difference between Sui and Aptos is.
I think the main difference is that we are open source, so it's kind of hard to know what implementation choice Sui took. I think at a high level, the approaches are similar. Deployment might be different. Choice of prover service deployment, pepper service deployment. GRAT16 ZKPs are also used by Suis as well. In terms of the consensus for the Google public keys, there may be differences there as well in efficiency, or although I'm not a consensus expert, so I can't say that them or us have a more efficient consensus. Yeah, is there a particular, if there's something in particular, I'm happy to discuss, but I think probably not too many differences.
There is a question in the questions area. We will come to that of Rajesh in a bit. But Nuh posted a question in the questions area, asking question to the cryptographer in you. You mentioned something about cosmic radiation for randomness. What are the golden standards of natural randomness in the real world? And are they not used as much instead of pseudo-random generation?
Oh, this is a great question, because I actually wrote a little paragraph about this in our randomness AIP. So I can point you here to my answer, and I don't have to recite it. But here I kind of give the spiel about real randomness versus pseudo randomness, and the TLDR is that the real randomness sucks, man. You can't verify it. You know, like if somebody tells you I got real randomness, it came from the sky, you're like, okay, thanks. How do I verify that, right? Pseudo randomness is actually what you want. I got pseudo randomness, it came from a VRF. Here's the public key. You can verify it. If you trust that the secret key was generated randomly and nobody else knows it, then you know it's unpredictable, right? And if you trust sort of the cadence at which randomness is revealed, so for example, on the Aptos network, every block we reveal a VRF and there's a cadence, right? And so the randomness is unpredictable because of that. So yeah, the TLDR is pseudo randomness all the way, but happy to be contradicted.
Fantastic. Moving on to the question from Rajesh, who's asking, have you guys explored proof aggregators?
Yeah, I think I was talking recently to somebody about this, exploring proof aggregation to make keyless transaction verification faster. Again, this is kind of a broad question as well. I don't know exactly what you have in mind when you say proof aggregators. People mean so many things. Sometimes they conflate aggregating with batching, which is not the same thing. One thing I want to say is that doing batch verification of keyless transaction signature doesn't really provide benefits, because if the batch verification fails, you still have to identify the invalid signatures, dismiss them, and keep the valid ones, right? So the benefits you get from batch verifications are easily circumvented by an attacker who just gives you one bad ZKP and then invalidates your batch. So batch verification is not really good for this. Proof aggregation, which is I have a bunch of proofs, I combine them into a single one. that'll just add latency to the whole thing. If I have to wait for other proofs before I transact, that's not good, right? I want to be able to compute my proof and send it to the chain ASAP. I don't want to wait for other proofs. Maybe if you have really high throughput and you don't really have to wait that much for proofs and your proof aggregation is extremely fast somehow by some magic, then yeah, maybe it would make sense, but I don't think we're there.
And Patrick has summarized this question also, so maybe that's going to make more sense.
So then it handles the entire ZK process and returns an address that represents the email on-chain. Once an on-chain users have the capability to choose which applications have access to their address. Yeah, so it's actually, it's not that users have the capability to choose which applications can have access to their address. You could implement it that way too, probably. I'd have to think about it. It's actually, and also it's not that the address represents the email on chain. It represents the email and the application ID, right? So if you recall from this picture, a keyless address is a commitment to the email address and the application ID, right? Not just the email address. And this is very important for security. If you didn't have the application ID in here, then when you sign into any website with Google, like medium.com, that website would have everything it needs to take over your address, right? So this is kind of important. Now, you could build it differently, and maybe you could build it in a way where you could do this thing that you wrote here, choose which applications can have access to their address. But that's not the way we've decided to do it. Yeah. All right. Let me do this flow really quickly because I want to give it a try also for my own benefit to see if it makes sense, and also I think it'll help put everything into context. So, okay, so here's kind of all of the moving parts. I have my user, I have Google, I have a DApp or a web wallet, and I have the blockchain. The blockchain has Google's pub key. It has the GRAT16 verification key for the keyless relation, and it has the training wheel pub key that the prover service uses to sign proofs to have this security mitigation against circuit bugs. So what does the user do? It generates an ephemeral key pair and a blinding factor for the ephemeral pub key in that nonce that it sends to Google. And then it goes to the DApp, and the DApp redirects the user to Google and sets the nonce to this EPK commitment using this blinding factor, right? And then the user goes to Google, authenticates using a password or an existing cookie. Maybe they're signed in already. Google starts assembling this message, which is called a JSON web token or a JWT. And it has a bunch of fields. It has a subscriber field. This is not the email address. It's actually a Google specific identifier, but we don't have to use the sub field. We can use the email field if you want. For this example, we use the sub. And there's an audience field, which is the application identifier that the user signed into, and the nonce field, right? And so Google assembles the message. If the user logged in successfully, it also signs the message. It creates this OIDC signature under Google secret key over the JWT and gives everything to the application. So the application has the JWT, Google signature, and maybe it has the ephemeral pub key and the blinding factor because it needed to assemble this URL. Now, what does the application do? It wants to compute the zero knowledge proof, but it can't because it doesn't yet have the pepper, right? The pepper is a secret input to the zero knowledge proof. So first it has to go to the pepper service, here called the guardian. And to go to the pepper service, it actually goes there with the JWT, with the signature from Google, with the EPK and its blinding factor. And what the pepper service does is it checks, hey, this is a valid JWT signature from Google, and the nonce field is set to this EPK using this blinding factor. And so I've authenticated that whoever sent me this has successfully logged in this user. And what I'm going to do is I'm going to parse this JWT's sub and odd fields, and I'm going to evaluate a VRF over them using my secret key. And I'm going to return the pepper to whoever sent me this JWT because by virtue of them having it, they're allowed to have the pepper. Yeah, of course, in the process, I'm also going to check the expiration date on the EPK and stuff like that. Right? And now the DApp has everything it needs to derive the address of the user. It has the pepper R, it has the sub, it has the odd, it can derive the address, and it's ready to engage with the prover service to compute the zero knowledge proof, right? So it's going to send the prover service the address, the ephemeral pub key, the GWT, the signature from Google, blinding factor for the APK, and pepper, which is blinding factor for the address. And what the prover will do is a couple of things. It's going to compute the ZKP, and then it's going to also check the keyless relation itself manually. And if it checks out, if the witness is valid, then it's going to provide this training wheel signature over the ZKP and the public statement to vouch for the fact that it also additionally verified the keyless relation. So it's not just that the ZKP verified it, it's also the prover service, right? And the relation, if you recall, as before, is that sigma G verifies on the GWT under Google's pub key. The nonce field is set to the APK as a commitment. The address is a commitment to the sub field in the GWT, and the auth field in the GWT using R as the randomness, right? So everything in red and yellow are witnesses. Everything in green is a public input. So is the address. It's a public input. And now the DApp has a zero knowledge proof, so it's ready to request signatures from the user. If this is a wallet DApp, it's not going to request signatures at all. In fact, it's just going to sign whatever it needs to sign. When the user clicks buy some token or swap some token, it's just going to assemble the transaction and sign it directly. But if the DApp is a web wallet, then it can display a prompt to the user. And what the user does is it compute the signature using the ESK over the transaction. And now the DApp, once it gets this ephemeral signature, it has everything it needs. It has a transaction, it has the ZKP, which delegates signing right to the APK, and it has a signature over the transaction under the CPK, right? So what does the blockchain do when it sees such a transaction and its keyless signature? Well, it first fetches the address from the transaction that's transacting on, and it's checking that the APK is not expired, like we touched before. It's verifying the zero knowledge proof on the public statement. So verifying that signing rights for this address are delegated to the CPK under Google's public key, vouching for this delegation. And it's verifying the ephemeral signature on the transaction and the ZKP. We also signed the ZKP with the ephemeral signature actually because of non-malleability reasons. And in fact, as you can see, I should have this here, but I forgot to add it. Lastly, it's verifying the training wheel signature on the proof and the public statement, right? And then if everything checks out, it executes the transaction on chain. And so those are the main steps. There are 2 signature verifications and a zero knowledge proof verification. And I think this is basically everything I wanted to say in the presentation. Happy to spend more time on questions.
Right on time as well.
Glossary. Oh, I saw this question.
Yeah.
Yes, there is a glossary. I made sure there is one because there's so many moving parts that without a glossary, you go crazy. And by the way, there's also a flow that is non-ZK. So it's a non-privacy preserving flow where the blockchain learns everything, and it's much simpler, right? So it's just Google signs, and then the user signs with the ephemeral secret key, and then you actually put all of the information on chain, the JWT and Google signature. So you leak everything, but there's no more prover service and there's no more pepper service. So there's no privacy on the address, right? So please take a look at that. And so this part of the terminology is for the simpler flow, and this part is for the ZK augmented flow,
Perfect. And just to follow up for Katya was asking for the glossary. I've already added slides to our hacker pack. I'm showing the link. So you will be able to download these slides and have a look directly into them as Alin shared them. And as for the recording of the session, it will be online in roughly the next 12 to 16 hours. Right. Any last questions, everybody? I see a new question just popped up in the questions area. Alin, maybe you can have a look as well. It's from No.
Questions area. Can
If you have
be enabled to?
I know it's we're running towards the end.
Yeah, it's fine. I can spend a few minutes. Not by an adversary. In our deployment, the rule is you have to pass a governance proposal to enable the non-ZK flow. So to the extent that the adversary controls enough stake in the system, it could do that. But that's kind of a reasonable assumption, I think. So no, it cannot be turned on by a reasonable adversary. Okay, so and I did answer this one.
Yeah, this one we already covered. Yes.
Yeah. All right.
All right. Well, that is it for the workshop on zkLogin architecture. Thank you, Alin, for being so thorough with everything. I think the slides are amazing. I think everybody will enjoy them, as well as those that did not manage to be here live. I'm sure there will be a lot, even more questions. But again, highly engaging and really amazing to see so much activity in the chat. And I think again a lot of great know-how being shared and throughout the workshop. For everybody that is here now, again, this is just the first workshop. We're going to be having another one later on today, which is going to be from Waydai from 1KX, and we will be covering the introduction to private transactions. So if you have the time later on in 2 hours, please make sure to tune back in. Invite should be in your calendar for another hour of amazing knowledge to be shared in the Explore Expander Bootcamp. Alin, maybe some closing words from your end?
Well, I think I'm very excited to present this approach to everyone, and I think it's really promising. I encourage everyone to think about it. Of course, it has drawbacks, but to consider reasonable ways of using this and consider reasonable ways to save your users from disasters with this approach. So happy to help in any way that I can. You can reach to me probably best on Twitter via DM. Yeah.
You preemptively answered the question that I was about to ask about what would be the best way to contact you. But yeah, everybody, you can just leave a DM on Twitter. Maybe you can share your Twitter handle in chat for everybody.
Yes, it's x.com. This.
Fantastic.
Yeah.
And for those watching the recording, it's Alin Ush, so ALINUSH 407.
Yes.
Fantastic. That is all for now. See you everybody in 2 hours for the next workshop. And yeah, Alin, you want to say something or not?
Oh, no, I just want to say goodbye, and please invite me to the private transactions talk.
Yes, I'll shoot you an invite immediately. Thank you all. Have an amazing day if you're not coming back. If you are, see you in 2 hours. Cheers.